All right, part two. So like I said last time, we talked about this wire, right? And if you had a current going through this wire I, you ended up with a field going around it. Now what I want to do is talk about a circular arc. And after we talk about a circular arc, we can talk about what happens afterwards. So we need, this isn't very good, we need this to be the center of that arc. And we want these guys coming in towards the center. That's so they don't affect the magnetic field here. So we want this to be the center. This is where we want our B, and this is where we want R. I'll call that capital R, the radius of this imaginary circle. Okay. So what's going to happen there? Well, you remember from last time that we had these magnetic fields, and I'm hoping they went this way, coming around here. And so you have these magnetic fields coming around this way here. So you have from here a magnetic field coming up right here, and here a magnetic field coming up right here, and here a magnetic field coming up right here. So all the way around here you're adding up the field from this one spot. So we're looking at just this center, right? And there's a lot of work that goes into trying to build something that's actually very homogeneous in that center, so you can do experiments and things like that with it. We won't talk about that. That builds up something called a Helmholtz coil, which is extremely useful for doing magnetic experiments. So this guy here will create a magnetic field, and that magnetic field is going to be mu naught over 2 times this theta. So I extend these out, the angle between these two wires here that are going straight out from the center is theta, over 2 pi, which means this is in radians. Right? If it's in, you have an angle in degrees, that's going to be 360 degrees instead of 2 pi. And then we have just I over, in this case, big R. All right. So you can see this is very similar to what we had previously, right, for the long straight wire, which was just mu naught over 2 pi times R I over little r, which was whatever the distance is along this path. So this big R is actually the distance from here to here as well, right? But it's only true at the center. It's not true anywhere else. Okay, only at the center of this circular arc, the imaginary circle on this circular arc. Okay? So that's what we've got there. And you can see the limit for this, right? If this is a circle, all right, is just mu naught over 2 over I R. That is, you just get rid of the pi from the previous example. So that is basically what we get for what would happen if this was an entire circle, which is usually what you do. Okay, so that gives us what we want to talk about in part 2, which is the field at the center of a loop, or at the center of an arc. The field, the magnetic field, is proportional to current and inversely proportional to radius of the arc. Okay. Another thing you can see is if you had a loop, or if you had a thing like this, this is where the coil is. If you have a coil with n turns, right, then Bn would be equal to just mu naught over 2 times Ni over R. Okay. Okay, so that's for a magnetic coil. That's an air coil without a magnetic core inside. Put a magnetic core in there, you actually get much, much more field, right? Especially if it's a high permeability magnetic material, which is something we can talk about in Zoom or something like that. It's not something that I'm going to ask any questions about. Okay, so I might ask you questions about this, but I want to ask you questions about why that is. I mean, it's just each time you go around here, you get another 2 pi, right? So if you have this relatively thin, that's what you get. So I guess that's A. For an N-turn coil, the field is proportional to N. All right, so if we had 2 loops, it would be just twice this field. If we had 3 loops, it would be 3 times this field. Okay, so that's what happens there. There is, however, one extra thing that I want to talk about, and that's a solenoid, which is something like this, where you have lots and 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 lots of turns on a coil, and it has some length L. This is getting really close to as N turns, it has a length L. This is a very special thing because it has a uniform field all the way inside. So everywhere inside of here has the same field. Right? And that's an interesting result that we can't actually prove here, but it's very, very interesting. So if you wanted to have a uniform field over the entire thing, over your entire experiment, what you do is you take a coil that's reasonably larger than your experiment, and you put your experiment on the inside, and you get a uniform magnetic field. For a lot of things, that can be a little bit difficult because you might want to, say, have something traveling through that way, for example. But most of the time, this is sufficient. And even in this case, if you make the gap small enough, the variations are so small that you don't care. So for that solenoid, the field is proportional to the density of coils, N over O. Okay, so that will be called B sub S for fun. Let's see, that's mu naught times I, right, which we've seen before, times the density, which is N over L. All right, so that's all you need for the inside of a solenoid. So my example will be a solenoid and calculating stuff about it in this approximation. Yeah, I think that's all we really need to know, is that we get a really uniform field in there because these things are so tightly packed. There's a way to do that with something called Ampere's law, which I think we talked about a little bit elsewhere, but no, actually we didn't. But there is something called Ampere's law, which we'll talk about in the next thing, I hope. We don't get to talk about Ampere's law. Okay, well, there's a similar law to Gauss's law that's called Ampere's law, and that's what does this. Talk to me about that in Zoom as well, because it's not going to be something we ask questions about on homework. All right, so this is about it. Yeah, that petered off a little bit, didn't it? All right, we'll talk to you later. We'll finish up with the field from a magnetic moment. All right.